Good afternoon. In this presentation, we'll be discussing coordinate systems. Coordinate systems are important when we define vectors and we conduct the system analysis related to robotics. The topics of our discussion today will be the definition of coordinate systems. We'll talk about Euler angles and also about vector notations. The motivation for our discussion is that typical robots, this is by the way the Scobot ER4U, which we'll be using in our lab experiments and programming. So a robot typically has several variables which are of interest to the engineer, such as motor torques. All of these are motors which actuate the robot arms, base velocity, how fast the base of the robot is moving, gripper force, how much force is exerted on an object, arm acceleration, the acceleration of various joints, end of arm accuracy, how accurate this robot is. All of these variables are actually vectors, and they have magnitude and direction in a three-dimensional space. And the three-dimensional space has a fixed coordinate system that is fixed to the shop floor, and many other coordinate systems which are fixed to the different parts of the robot. The inertial coordinate system, which is designated by x0, y0, and z0, is fixed to the floor. It's not moving at all. It is a Cartesian coordinate system based on a right-hand rule, meaning that if you rotate x towards y, like we rotate in a screw, the screw will advance in the z direction. Rotating from x to y will advance a right-hand screw in a z direction. So this is our inertial coordinate system. If you look at a different coordinate system, which is rotated an angle psi with respect to the inertial coordinate system, and we designate that in red, and we call it x1, y1, and z1, you see that z1 has not changed. It's basically the axis of rotation of the x1, y1 coordinate system, and we call that angle a yaw. And we designate it with xi because it's easy to remember. I like it. Y and yaw is similar. And this is the first angle of the Euler angle set. Now we could generate another angle, but by taking the x1, y1, and z1 and rotating it about the y1 axis. So the y1 will become y2, and that rotation, which is phi, and I designate that phi close to pitch. This is rotation about y1. This is the pitch of the rotation. And it generates x2 and z2. And the last coordinate system is the roll, and if we take the x2, it looks a little bit complicated here, and we rotate it about the z2. In other words, z2 now is fixed, and we take x2 and we rotate it an angle rho, and rho is standing for roll. It's the third Euler angle. Then we're getting x2 becomes x3, y2, which was here, becomes y3, and z3 stays the same. So these are the basic coordinates that we show through Euler angles and different rotations. And this will be important when we later on discuss coordinate transformation. If you look at the vector representation in a coordinate system, so let's take a look, for example, at the inertial coordinate system, x0, y0, and z0. If we take a top view of this coordinate system, we end up with x0 and y0, and z0 is coming out of the screen. And if we have a vector, which is represented here by letter r, to a certain point in this coordinate system, which we represent as a, this vector has two components. We call them r, x0, because this vector is resolved along the x0 axis. And we have also a coordinate of resolution over here of r, y0. These are the two components of vector r, and we can designate in upcoming discussions in the following way. We can call this vector of point A in coordinate system 0, r, a0, and we have the little bar on top to designate it as a vector. We can also define it for a shortcut as just r in some cases. We can show it in two parentheses as a vector, where r without the head is a scalar and the two parentheses indicate a vector. We can take the two parentheses and we can also put the x, y, and z components of that vector in this way. It's also identical definition. We can also write it as the component. This rx0 is r times the cosine of theta. We can write it over here for the x0 component. This component over here is r times sine of theta. So we can write it here for the y component. And the z actually has 0 component because it's a planar description of this vector. So the z component is 0. And sometimes to save space, we can also write it as r times cosine of theta this way, r times sine of theta this way. So this basically concludes our discussion of coordinate system presentation, and we'll be using it in upcoming discussion. Thank you.